Okay, so in the last video we explicitly explored a particular type of matrix called a permutation matrix, which is about rearranging rows or columns. And you'll remember I've mentioned previously that obviously, you know, if we just want to rearrange the columns in a matrix where there's only 3 columns, that's not a particularly difficult process. But again, we're thinking about the basics of processes that are used in much larger data sets. Okay, so we're thinking about it as a process rather than, you know, oh, why would I do it this way when I could just do that by hand? Okay. And yes, in this instance, if you're understanding what the permutation matrix does, then yeah, you can just rearrange it. But the point is to have some understanding of why the permutation matrix is doing that. So what we want to look at in this video is 2 further kinds of matrices, dominance and communication matrices. And they're sort of connected in that they're about connected wasn't a good word. They're sort of similar in that they're about connections between people or places or towns or whatever the situation might be about. So we've previously seen how matrices can be used to represent networks. So when we looked at that a couple of videos ago, we looked at, or I think it was the first video actually, we looked at undirected networks, which means that there's no arrows on any of these paths. If there's a line joining A and C, like this line that we're seeing here, that means that you can get from A to C and you can also get from C to A. Okay, and that means that we get symmetry in our matrix, because if this is from A, B and C, from A, B, C, D to A, B, C, D, then we are seeing that there's one way to get from A to C, but there's also one way to get from C to A. So we're seeing that symmetry because the paths are all two-way. So what we want to look at in both dominance and communication situations is the potential that some of those links are one-directional links. Okay, so we call that a directed network, where yeah, there's going to be arrows on the line lines between the towns or the people or whatever the thing's about, which indicate the direction of flow, whether that's communication or traffic or roads or whatever. Okay. When we talk about one-step or one-stage paths between the towns on this network, we're talking about how the numbers in the matrix are representing the number of ways we can get, for example, from town A to town B in just one step. Okay, so for example, just let me have a quick look. It's not possible to get from town B to town A, okay, in one step. We can do it, no, actually in this case we can't do it in 2 steps, but if it was possible to do it in 2 steps, that's fine, but it doesn't go in our one step or one stage. We call it the adjacency matrix. So an adjacency matrix is literally just representing one step or one stage paths, okay, between things. We might want to consider the 2-step or 2-stage paths. For example, going from A to C to D would be a way, so travelling from town A to town C and then to town D, whilst we can get directly from town A to D, sorry, but that would be a 2-step path. And there'd be another 2-step path this way, and there'd actually also be a third using the alternate path between A and B. Okay, so it would be 3-step, 2-step paths between town A and town D. And we can calculate the 2-step paths by taking our 1-step matrix, our adjacency matrix, and squaring it would calculate the number of 2-step paths. And that's where we're seeing this number 3 here in the top right. Okay, to get from town A to town D, we have 1, 2, and 3 ways of doing that in 2 steps. There is one way of doing that in 1 step, but where the m squared matrix, sorry, is giving us our 2-step paths. Now again, the original matrix here defined for us, because we have the diagram, it defines which way the matrix is working. Okay, so I would use, for example, the 2 here is helpful because that's telling me how I get from A to B. So that means if this is A, B, in fact I'll write them on the right hand side just so there's room. If this is A, B, C, D and A, B, C, D, what we're seeing is the numbers here are saying if I go from the row to the column. Okay, there needs to be information in the question to identify how to read the matrix. Okay, and often it will be by writing something like this on the side. So we're going from this place to this place. Okay, in this case the diagram enables us to work out that we're talking about from the city in the rows to the city listed in the columns. towns. And so that means that same process follows into the second matrix. So we're going to town A, B, C, or D from town A, B, C, or D. So in this instance, the 3 is telling us there are 3 two-step paths to get from town A to town D. This 2 is telling us that there are 2 two-step paths to get from town A to town C. Okay, so from town A to town C, we can go to B and then to C on that path, or from B and then to C on the alternate path between A and B. Okay, there is 1 two-step path to get from town B to town D. Okay, and that is town B to D. We can go via C. There's the 1 two-step path. Okay. So squaring the adjacency matrix, and the adjacency matrix displays 1-step paths, but squaring that enables us to see the 2-step paths. We could also consider, 3, 4, 5, 6, etc. step paths by finding the cube of the adjacency matrix, or raising the adjacency matrix to a power of 4 or 5 or 6, etc. But obviously in a quite small network here, we would see that there just really aren't any 2 or 3 stage or 4 stage paths, etc., or it becomes pretty trivial. So again, we're thinking about much larger systems. If we wanted to consider the total number of 1-step and 2-step paths within the network, we could, for example, add those 2 matrices together. So M is giving us, that's the original adjacency matrix, that's all the 1-step paths. M squared is all the 2-step paths. So by adding those together, what we're now getting is the total number of ways to get from each town to the other towns in either 1 or 2 steps. Okay, so there are 4 ways to get from town A to town D using either 1 or 2-step paths. Okay, so let's have a look at some examples. So part A, construct a matrix to show the number of 1-step paths. Okay, so again, let's be clear with ourselves about the direction. We're going from this city or town, A, B, C, D, and then we're going to this city, A, or town, A, B, C, D. Okay, so from town A to town A, in 1 step, not possible. The only way that would be possible is if we had a loop that looked something like this. That doesn't tend to happen on road network matrices, but it happens in other kinds of matrices. So no way to get from A to A in 1 step. From A to B in 1 step, there is 1 path. Okay. From A to C in 1 step, there is also 1 path. From A, I need a bigger matrix. We've got 5 cities. My apologies. All right, let me just erase this and start again. Sorry. I didn't look far enough in advance. Okay, so let's think about, right, a bit smaller. We're going to have A, B, C, D, and E. And we're going from these. Okay, and here we're going to have A, B, C, D, and E. And we're going to be going to those cities at the top. I'll just make that bracket a bit bigger. Okay, so from A to A we found there was none. From A to B there was 1. From A to C there was 1. From A to D there is 2 paths. 2 1-step paths. And then from A to E there is 1. Okay, from town B to town A, it's not possible to get from B to A in 1 step. So no path. From C to A, again, not possible. Sorry, wrong way, sorry. From B to B, not possible. From B to C, no, can't get across there. From B to D, nope, can't get there. B is not a great place to be, can't get very far, but we can get from B to E. So from town C, can we get to A in 1 step? No. From town C, can we get to B? No. C to C, no. C to D, yes, there's 1 path here for that, but C to E, no, there's not 1 direct path. So B and C, not great, can't get very far. Town D, so from D to A, there's 2 paths that come from A to D, but it's not possible to get back that in this direction. So there's no way to get from D to A in just 1 step. D to B, no. D to C, no. Again, there's a path coming in the other direction, but we can't get back that way. D to D, no, and D to E, no. Okay, D is definitely the worst place to be. All the roads are incoming. Once you get there, you can't ever get out again. And again, I'm talking about roads just because that's what we're familiar with. This might not be roads. This might be communication, phone lines or directions of communication. This might be, we'll talk more about dominance later on, but this might represent 5 teams in a basketball competition and who wins against who. So the complete row of zeros in D might be representing the fact that D didn't beat any team, for example. Okay, so lots of different things the network might represent. Here we're just looking generally at how to form the matrix. Okay, so I'll continue to talk about them as if they're towns and roads, just as a sort of give us a bit of does this make sense kind of idea. Okay, so last thing is from A. So from A to E, no, we can't. Sorry, from E to A. My apologies. From E to A, no, we can't get that way. From E to B, no. Again, there's a path, but it goes the other way. From E to C, no, there's no path at all. And from E to D, yes. E to D, yes, we can get that way, and E to E, we can't. Okay, so this is our adjacency matrix that shows the one-step paths. Constructor matrix, I'm going to call it, I won't call it A because we've got a town A, I'm going to call it M again like we did previously. But M is not the conventional letter, I'm just using M for matrix. Constructor matrix to show the number of two-step paths. So the number of two-step paths is M squared. So we'll get our CAS to work out what M squared is. So we need, this time, a 5 by 5 matrix. We'll put our numbers in, so 0, 1, 1, 2, 1, 0, 0, 0, 0, 1, 0, 0, 0, 1, 0. All zeros in this row. And the bottom row we've just got a 0 and a 1 in the fourth column. Okay, so that's our matrix, and then we're going to square that to get the number of two-step paths. Okay, so again, I'm just going to annotate it so we can be clear about what we've got. A, B, C, D, E. So we've got 0, 0, 0, 0, 2, 1. We have 0, 0, 0, 1, 0. And then everything else is zeros. Okay, so let's have a quick look at what this means. So particularly we've got a 2 here, but going from A to D. Okay, so there are two-step paths to get from A to D. And that would be to go via C, would be one of them. And the other one would be to go via E. Okay, that's the two-step paths. It says that there are no two-step paths out of D at all, okay, and that's because there's no one-step paths out of D at all. But there's also no two-step paths out of C at all. Now C at least have one way to get out, okay, but once you get to D, you can get to D from C, but then you can't get anywhere from D. So there's no two-step paths out of C, and similarly for E. So E, there's one-step path out, but it gets you to D, and there's no way to get out of D, and so there's no two-step paths out of E either. For example, if we have a look at the number 1 here, so that is from B to D. So from B to D, there's one two-step path, and yes, that is to go via E. You'll notice that there weren't any direct paths from B to D, but there is one two-step path, and that comes out when we do the multiplication. Okay. All right, so determine the number and name of the one-step paths from A to D. Okay, one-step paths from A to D. There are 2 paths. Okay, so the one-step paths we're looking back up in this matrix, that's A to D, and those 2 paths are literally, so by naming them, we're just naming the path. It's literally A to D and A to D. It's just that there's 2 different paths. Okay. Determine the number and name of two-step paths from A to D. Okay, so in this instance, this time we're looking now here, two-step paths from A to D. Again, there are 2 paths. All right, and the first one was going to be ACD, A to C to D, and the other one is to go via E, A to E to D. Okay. All right. we want to take this now a step further and think about it as dominance. So if an edge or path in a directed network moves from A to B, then it can be said that A is dominant or has greater influence over B. Okay. So as I said to you, as we were filling in this original matrix in this example, I was like, oh, C's a terrible place to be. Oh, D's an even worse place to be. So it's clear just looking at that really A is the most dominant town in this network. You can get from A to more places. In fact, you can get everywhere from A, whereas the others, it's quite limited where you can move. So in that network, we can see informally that A is the dominant node we refer to networks. A is the dominant town or city in that particular network. So sometimes we might wish to find the dominant vertex in a network. So that is the vertex that holds the most influence over all other vertices. So that might just be that it has the most road connections. It might be that it has the most friendships if it's about people. It might be that it has the most wins if it's representing a sort of sporting competition. So sometimes, as I said, we can identify the dominance by inspecting the network. But generally speaking, if there are more ways to get from A to B than there are to go from B to A, then A is the dominant vertex. So in the one we looked at, as I said, it's really clear that A is certainly the most dominant network. But it might not be so easy to determine just from inspection. Okay, so in these cases, a more formal approach using matrices is used, and we do this by calculating a dominance matrix. And a dominance matrix, given the size of the matrices we're dealing with here in further maths, is about considering the total number of 1- and 2-step pathways in the network. So we've already talked about that. Remember, M is our 1-step pathways, M squared was our 2-step pathways. Adding them together is giving us the total number of 1- and 2-step pathways. Then if we add up the rows here, which is what we've done here, this is the total number of ways to get out of A. Okay, so the arrows away from A. So that's where A is dominating other cities. So it's not about adding up the columns, because that would be saying how many cities can come to A. Because remember, this was these were all about 2. Okay, so it's not dominant if the arrows are coming towards you. It's dominant if the arrows are going away from you. So we want to add up the rows. Which would in this instance be saying there are a total of 9 1- and 2-step paths away from A that can take me to other cities in the network. There are only 3 1- and 2-step paths that take me to B, and there's only one that take me away from B. There's only one that goes away from C, and there are no paths at all to get away from D. So D is definitely the least dominant place in the network. Okay, so that sort of confirms our sense of what we could see informally in the network. So again, we might need a process if the network's not quite so obvious. We can also recall that in order to calculate this sum, we can use a summing matrix, which in this instance would be to multiply by a column matrix of 1s, and that would produce our sums. But in practice, we're not ever going to be dealing with matrices that are so large that you would need to use a summing matrix to calculate the sum of each of the rows there. Okay, let's have a look at an example here. The results of a round-robin basketball tournament are represented in the network shown opposite. So an arrow, and we've got a little key here defining what's happening. An arrow from A to B means that A beats B. Okay, so A is dominant over B. In the context of this problem, that means they won. By inspection, determine the dominant team that is the winner of the tournament. Sorry, that should be an of. Okay, so we want to have a little look. So A beat 2 other teams. They beat D and they beat B. Okay, so there's 5 teams though. So they played 4 and they only won 2. So they're not immediately particularly dominant. Let's have a look at B. B only beat 1 other team, D, so they're not particularly dominant. So A beat 2 teams, B beat 1 team. C, let's have a look. They beat A and D and B and E. So C beat everyone. So looking at the network, it's pretty clear that C has to be the dominant team in the situation. So if C beat everyone, everyone else has to have at least lost to C. So there's no point in considering any further. So sorry, that should be an of. So C beat all other teams. So is the dominant team. So we'll have a look at the process of checking that, and hopefully we see that we're correct. Okay, so construct a one-step dominance matrix, D, showing the one-step dominance between the teams. Okay, so let's construct our matrix D. Okay, again, we're going to have A, B, C, D, and E. We're going to have A, B, C, D, and E. And I'm going to use the rows as being the winner. Okay, so A beat B would mean a 1 here, and therefore it would mean a 0 here because B didn't beat A, for example. So there's still some symmetry in these matrices, it's just not the same numbers. Okay, so A doesn't play A, so there's going to be zeros on the leading diagonal. B doesn't play B, C doesn't play C, D doesn't play D, and E doesn't play E. Okay, did A beat B? Yes. That means that B didn't beat A. Okay, did A beat C? No. But that means therefore that C beat A. So I would work this way so that for every decision you're making, you should be able to put two numbers in. So did A beat D? The arrow around here, yes, A did beat D. A beat D, yes, and therefore D didn't beat A. And did A beat E? No. So therefore E did beat A. Okay, B, C, so did B beat C? No, so that means that C beat B. Did B beat D? Yes, that's that one there. B did beat D, which means therefore that D did not beat B. And how about B and E? So B did not beat E, which means that E did beat B. Okay, C and D, so C beat D, which means that D didn't beat C. And C beat E, which means that E didn't beat C. And last one is to consider D and E. D did not beat E, which means E did beat D. Okay, so that's our one-step dominance. We then want to construct the two-step dominance, so that is D squared, by squaring the matrix we've got in part B. So I'm going to enter in my dominance matrix. It is 5 by 5. Okay, 0, 1, 0, 1, 0, 0, 0, 0, oops, sorry, that's a 1, 0, C beat everyone except themselves, 1, 1, 0, 1, 1, D didn't beat anyone, so we would clearly expect them to be the least dominant, and E. Now, I want to make a clarification here. Whilst it's helpful to also think about D squared, if you've got a clear order just looking at the one-step dominances, then you wouldn't go to D squared at all, okay? So I suspect, in fact, this example, finding D squared is a step beyond what we would need to do. So I apologise actually that this isn't the best example for this. So if I looked at my one-step dominances, I see that Team A beats two other teams, so I'm adding up the row there. Team B beats only one other team, Team C beats 4 teams, Team D beats no teams, and Team E beats 3 teams. So actually we have a clear dominance just from the one steps, and so we wouldn't actually calculate D squared in this instance. I'm going to do it because the question asks us to go through that process, but you would only go on and consider D squared if you had a tie, say for example. So if both A and E only had 2 wins, for example, then we would look at D squared to see, but we would probably actually only focus on A and E. We would probably only look at between A and E, who has more two-step dominance out of those two, given that they were tied on one-step dominance. So this idea of just blindly adding these two together and going based on that is actually a little bit flawed in practice. So you would actually consider how much one-step dominance does a team have. If from that you can determine the order, which in this case is C, E, A, B, D, then you're done. Okay, that's the finishing order of the competition. If from that you've got 2 teams or 3 teams or 4 teams that are tied, then you would look at the two-step to split those ties. Okay, you wouldn't allow it to change the order of anything else. Okay, so yeah, this process, I have to say, is a little bit the explanation, the blindly just adding together d and d squared is a little bit flawed. Think about what you're learning at each step and then make your decisions from there. So at this point here, we can determine the order. And hopefully we'll see that adding in the second step dominance doesn't change the order. So the dominance here would be C and then E and then, so C and then E and then A and then B and then D. Okay. Let's have a look at d squared. I've created the matrix, so I'm going to square it just to interpret those numbers that we've got there and what that actually means in this context. So we've got 0, 0, 0, 1, 0, 0, 0, 0, 0, 0, 1, 2, 0, 3, 0. Okay, so what we're seeing here, remember this is from A, from B, from C, from D, from E. So we're seeing that C continues to have quite a lot of two-step dominance. They're clearly the dominant team in the competition. Team E also has quite a lot of two-step dominance. So even if, say, for example, A and E had been tied on one step, it might be revealed at this stage that E has more two-step dominance. So let's think about what two-step dominance means in this context. So let's think about this. We're seeing that E has two different two-step dominances over D. So this is column D. Okay, and that is because E beat D directly, okay, that's fine. But E also beat B, who went on to beat D, okay. In addition, E beat A, who went on to beat D. So E beat two other teams that then beat D. So they have, Team E has two sets of two-step dominance over E has two sets of two-step dominance over Team D. And again, though, that only becomes relevant if there's a tie. The fact that E beat D directly is still the most important thing. Construct the matrix D plus D squared. Okay, so D plus D squared, and sum the rows to determine the rank order of the teams in the competition. So if we do, I'm just going to remove that squared. So that's D plus D squared. We now get this, but we could add our matrices from parts B and C by hand just as quickly as we can with our CAS. So we get 0, 1, 0, 2, 0. We get 0, 0, 0, 1, 0, 2, 3, 0, 4, 1, 0, 0, 0, 0, 0, 1, 2, 0, 3, 0. Okay, so we're getting sum the rows, so this sums to 3, 1, 5, 9, 10, 0, and 6. Okay, and so that doesn't change the order that we had from the first step. The dominance is still this. Okay, if it did change the order, that's irrelevant. Okay, we actually, as I said, this isn't a good example. I'll change this example in future to we have at least two teams that are tied at the first set of dominance, and then we need to look at the second set. All right, so again, I'd be careful about just blindly observing this. The textbook certainly suggests that as a process, but I would think about D individually, how much one-step dominance is there. If you don't have a clear order at that point, then go to D squared and use D squared to separate the teams where there are ties based on D. Okay, so use this process that the textbook outlines with a bit of caution. Okay. All right, I then want to look at communication matrices. So a communication matrix is also a binary matrix. Sorry, not also. A dominance matrix doesn't have to be binary. Binary meaning we just have zeros and ones. In which we have links in communication. So unlike roads or, I don't know, maybe a sporting competition where you play each team more than once, it's not possible, if you're just talking about communication, can A communicate with B? You either can communicate or you can't. It doesn't really matter how many mechanisms you have to communicate. So either yes, number one, there is communication or in that direction, or B, or no, zero, there is no communication in that direction. So for example, here we have a communication network, and we're seeing we've got two-way communication between A and B. So again, thinking about sort of the matrix should really be labelled. So from A, B, C and D and to A, B, C and D. I would label them on this side, it's just a bit cramped. So from A to B, there's definitely communication, so that's this one here, but also from B to A, there's communication, so that's this one here. In this instance, it's not all two-way communication. So say, for example, you can communicate from D to B. So from D to B is this one here, but there isn't the corresponding, sorry, let me use a colour so you can see what I'm talking about. So from D to B, we can communicate, but we cannot communicate from B to D. So we don't necessarily have that symmetry where we just have one-way paths in communication. Okay, so we've got this communication matrix. It should be noted that the leading diagonal contains only zeros, since a communication link from A to A is irrelevant. That was the same with the sporting competition. Team A beating themselves is irrelevant, so we have all zeros in our leading diagonal. We can also consider two-step links. So whilst C can't directly communicate with A, okay, so C to A is a 0 up here, we see in the two-step links we get a 1 here. And that's because it is possible for C to communicate with A by relaying a message via B. So we can go from C to B to A, but we can't get directly from C to A. The other thing to note is sometimes when we calculate the two-step matrix, we get numbers in the leading diagonal which are not relevant. They're called redundant links. Okay, so what we're seeing here is that just through the maths of squaring, we're now seeing potentially that it looks like there is two ways for B to communicate with themselves, which, you know, if you look at the network, is correct, because what it's looking at is B can communicate with A that can then communicate back with B. B can communicate with C that can then communicate back with B. But they're pointless, because if B wanted to communicate with themselves, they wouldn't send a message via somewhere else. So if you're going to go to a next step, let's say we wanted to calculate C cubed, where we had if you had lots more nodes, you know, if we had 20 different people in this network, and we wanted to look at C cubed, how many three-step ways of communicating are there? What we would do before we calculated C cubed is that we would think about getting rid of these zeros here before we then multiply by C again. Okay, it's getting rid of those redundant links before we then multiply again. Okay, otherwise they get counted in, you know, if you're looking at a three-step link, you get counted as, for example, let's have a think about this. So from A to C, there would be a three-step link, because you can go from A to B and back and then to C, okay, which isn't really a three-step link. So you need to be a bit careful about redundant links, but in all honesty, in the size of the networks and matrices we're dealing with in further maths, they don't really become relevant. We don't really go beyond two-step links, in which case that just means essentially ignoring the numbers that are happening there. Okay, let's have a look at an example. Consider the communication matrix shown opposite. The rows represent where the communication comes from. Okay, so from these places or people, and the columns represent where the communication goes to. Okay, so who can C talk to? So from C, C can talk to A and to D. Okay, so C can talk to A and D. Who can B receive calls from? So who can communicate to C? So this is the column we're interested in, sorry. So the only person that B can get messages from is D. Who can call only one person? So that looks like from B, they're the only person with just number 1 in their row. So B can only call D. So person B can only call one person. Who can receive calls from everyone? Looks like person D can get calls from everyone. Obviously they can't get calls from themselves, but that's irrelevant. But they can get calls from the other 3 people in their network. So person D. Okay, so the work today is exercise 11F, questions 3 to 7.